What is the reason for learning object-oriented design patterns? Learning design patterns is like learning jujitsu techniques. You've probably seen self-defense or jujitsu technique demonstration videos on YouTube. When you consume such contents, you can learn various methods to suppress your opponent or defend yourself by utilizing different characteristics such as human joints, the principle of the lever, and the center of gravity. As you explore various technologies that utilize the structure and mechanics of the human body, you will have realizations like, I've used it my entire life, but I had no idea I could do these things with my body. Although it's not as complex as our bodies, object-oriented programming languages offer functions that go beyond simply using classes and objects. Concepts such as inheritance, polymorphism, and encapsulation may be difficult to understand how they can be effectively used in practice on your own. Therefore, there are many people who have learned object-oriented languages like Java, but don't know how to utilize them, so they use it almost like a procedural language. Object-oriented design patterns, like the techniques created by jiu-jitsu masters through countless practical experiences and research, are systematically organized knowledge based on various problem-solving experiences stacked up by software developers. These patterns analyze real-world cases accumulated over decades to offer the most effective and validated object-oriented solutions. Through various design patterns, you can learn ways to more easily solve complex problems and make or fix programs more conveniently. Learning design patterns allows you to use the features of object-oriented languages more effectively in real situations. In other words, you'll be able to use object-oriented programming languages in a way they are intended to be used. You can write cleaner, easy to maintain code, and design more understandable structures for team collaborations. I hope this course will be truly useful and enjoyable for all those who take it. Now, let's get started with Jelko's object-oriented design patterns. In the upcoming videos, we're going to start with what object-oriented programming is and explore various concepts associated with it, as well as object-oriented design patterns. Just like you need to learn various ways of parking to learn driving and get a license. Nowadays, it's almost essential to have knowledge of object-oriented programming for programming. Programming languages of today, except for a minority like C or assembly, all include object-oriented programming concepts and features, and it has secured its place as a fundamental component of software development. Therefore, whichever modern programming language you choose, in order to learn coding, you have to climb this mountain called object-oriented programming from the start. However, for those learning programming for the first time, object-oriented programming can be an unfamiliar and difficult concept. In this video, we'll explore what object-oriented and its key components are, solely through analogy, without using any code. Those of you who are learning to code for the first time will grasp what object-oriented programming is and why it is used in programming. For those who have already learned about object-oriented programming, and for those who are going to study OODP, through the explanation in this video, it will be a time to look again, or perhaps from a new perspective, at the important components of object-oriented programming. One thing to remember is that object-oriented is a complex concept that cannot be metaphorically compared to anything in reality. Therefore, I would like to mention that what you will see in this video is just one of the many aspects of object-oriented programming. Let's think of software development as building a medieval castle. The developer is a lord who must write his instructions in documents to construct a castle. These documents of instructions are the programming codes, and the laborers to be mobilized for the construction are the resources of the computer. The programming code includes instructions on what to order the laborers to do. The most primitive method is to list each command to the laborers. Go to the forest and cut down trees. Trim the cut trees into timber. Make a beam with those timbers. Mix cement and sand. Pour water and mix it to make mortar. Stack stones in this space using the mortar. Just like this, we're giving each and every instruction one by one. These instructions will continue endlessly, and similar content will be repeated countless times. A code written in this way is very verbose and has a lot of redundancy, which is inefficient. It is also difficult to analyze and modify this afterwards. How can we improve this? First, we can group certain units of tasks together. The first 3 instructions can be bundled into make wooden component. You can bundle the next 3 instructions into lay stone. In programming, a unit that groups such repeatable tasks is called a function. Its meaning is different from the function in mathematics or functional programming, but they have a common point in that they include one or more processes. This way, the functions we've created can be reused as much as needed to write more succinct and efficient code. Now developers can command their laborers, alright, from now on, make wood component, this time, lay stone, and so on. This function is a feature available not only in object-oriented languages, but also in non-object-oriented languages like C. Up until now, we've been dealing with procedural programming. This means it's not object-oriented programming. We have improved the reusability and efficiency of our code with functions. But as the size of the software grows, this alone will not be enough to manage code complexity. This is where the concepts of object-oriented programming come into play. We are going to define roles. These roles are called classes in object-oriented programming. In the process of building a castle, such classes as the carpenter, mason, blacksmith, and engineer are mobilized. Basically, we're defining jobs. In this tutorial, we're going to call them classes and roles. Each class has its own data and functions defined for the role. This data is referred to as attributes, properties, or fields. In this video, we will call it attributes. These attributes are the state each of these laborers responsible for this role possesses. And the functions in the class are called methods. These are the actions these laborers can perform. For example, in this carpenter role, tools used by the carpenter and the blacksmith who makes those tools are attributes, and the work the carpenter does, namely make wooden component, is defined as a method. The key here is this method. Each role assigned laborer takes on the responsibility for this action. Attributes are just the data needed to perform this responsibility. Masons have the responsibility of stacking stones, blacksmiths have the responsibility of making tools, engineers have the responsibility of engineering in the form of a method called function. In this way, in object-oriented programming, before starting the construction of a castle, these roles and their respective responsibilities are first designed and defined. Then you tell the laborers, you are carpenter 1, you are carpenter 2, you are the mason, you all are blacksmiths. Like this, after assigning everyone their roles, you make them work. Imagine you're overseeing manual laborers to build a castle. Rather than just ordering them around as I initially showed, you will easily understand that this method of defining roles and assigning them to laborers is a much more systematic and manageable way. The code of object-oriented programming is usually modularized like this, separated by classes. If there's a need to modify the program, you can just find and modify the corresponding class. It also becomes possible to reuse one class in multiple programs.
So, you're saying we can use the carpenter class later in programs that build houses or bridges?
Yes, that's right. We call the laborers assigned to this role that we call a class, an instance, or an object. These objects are chunks of data that have data about the attributes and methods they are assigned according to their role. Because these data are stored in an object, people often misunderstand objects as pockets for putting data. But, as I mentioned earlier, what's important is this method, that is, responsibility. An object is a result of assigning a class or a role to certain memory resources, making it an entity with responsibility. If you haven't learned programming yet, you can stop watching the video here. Through this analogy, you should be able to grasp roughly how object-oriented programming makes a computer work, and why it is a method that can make software more stable and efficient. From now on, this is for those of you who are learning object-oriented programming or a programming language that supports it, and for those who will watch the videos about object-oriented design patterns. You will be able to understand the various concepts of object-oriented programming, which were challenging to grasp more easily. Even if you don't understand what the explanation is trying to convey, please keep watching without feeling burdened. As you look at the code in the following videos, you'll easily understand what it meant. We're going to cover features common in most, but not all, object-oriented programming languages. First, let's learn about encapsulation. These classes usually do not work alone. They perform complex tasks through cooperation with other classes. For example, carpenter objects have a designated blacksmith object as an attribute in this way. They call the methods of the blacksmith object to order the tools they each use. The important thing here is that the carpenter object doesn't concern or interfere with how the blacksmith object fulfills this responsibility of forge tool. You see these plus and minus signs in front of the properties and methods. These items marked with a minus sign are private, which means they're hidden from the outside. So, objects of other classes cannot read or modify this data. This is called encapsulation. No one should interfere with what temperature of fire the blacksmith uses and which anvil he uses. The carpenter simply orders the necessary tools from the blacksmith, and the blacksmith makes and hands them over in his own way. In this way, by making sure each class is only concerned with the responsibility it's undertaken, you can reduce the complexity of the code and ensure flexibility. Typically, each class only exposes certain methods to the outside, using them as a communication interface with other classes. When writing the code for the carpenter class, developers do not need to consider how the blacksmith class is implemented. They only have to call this forge tool method, which the blacksmith has made public. And regardless of how the mechanism of the blacksmith class running forge tool changes later, it doesn't affect any other class's object calling it at all. External factors only get the output of the task through this public method. Think about how tangled and complicated the code can become when you allow classes to interfere in each other's affairs. You might guess why we encapsulate once you envisage it. Next, let's get to know about inheritance. As tasks become complex and voluminous, the types of roles required also increase. For example, in addition to creating wooden parts like ordinary carpenters, there could be a construction carpenter capable of using them to construct wooden structures. Similarly, a stone sculptor who can carve stones in addition to the work that an ordinary mason can do, and a bricklayer who stacks bricks instead of stone, these roles can be defined. Then, shall we define them as separate classes just like we defined the carpenter and the mason? We could do that, but there are two disadvantages. The first is that the code becomes verbose because there are overlapping parts. The construction carpenter class is a class that adds its own methods to the attributes and methods of the existing carpenter class, hence there is such duplicated code. It would be inefficient if we have to write these one by one every time we create a derived class, and if there are changes in the common features later, we would have to apply these one by one as well. The second is that no correlation is created among these classes with a common denominator. There are classes that share attributes and methods, but these commonalities cannot be reflected at all in programming. Here, the concept of inheritance in object-oriented programming can be very useful. A class can pass over attributes and methods to another class. When we set the construction carpenter class to extend from the carpenter class, the child class, construction carpenter, inherits the attributes and methods of the parent class, carpenter. The developer then sets this relationship and writes any additional attributes or methods that the construction carpenter class will have. This can significantly reduce the amount of code. Similarly, the mason class can have the stone sculptor and bricklayer classes derived as child classes. The stone sculptor class also has its own additional method, in addition to the attributes and methods inherited from the mason class. On the other hand, the bricklayer on the right inherits its parent's methods in a different way. The bricklayer doesn't follow the laystone method the way the parent class handed down. When an object from the mason class executes the laystone method, it simply stacks stones. However, as you can tell from the class name, when the laystone method is executed in bricklayer object, it stacks bricks. So, child classes are created to execute specific methods in a different way. Overriding the parent's method in the child's way like this is called overriding. Inheritance is not only for creating a class with added properties or methods, but also for creating a class that modifies the way specific methods operate. Of course, you can do both. The benefits of inheritance aren't just about reducing code volume through duplicate removal. It's also about being able to group different classes into one category. Construction carpenter is a type of carpenter, and a stone sculptor and a bricklayer are types of mason. This means that a construction carpenter can fit into a place where a carpenter can, and a stone sculptor, bricklayer, can fit in a place where a mason can. For example, arrays or lists that can contain mason objects can also hold objects of stone sculptor and bricklayer. In other words, a parent class can also serve as a category that groups child classes together. And this category can act as a standard that determines which classes can be used in specific positions. There are classes that solely aim to become a category. This engineer class is an abstract class. Abstract classes cannot create instances or objects by themselves. Just like there are no animals that people only call mammal or reptile. We do not assign laborers just an abstract role called engineer. It should be more specific. This class has a method called engineer, but it is only defined by its name and does not specify what it does. Hydraulic engineer and defense engineer classes are child classes of this engineer abstract class. Workers can be assigned roles as objects of these more specific child classes. They can become hydraulic engineers or defense engineers, but they cannot be just engineers. And the specification of what this engineer method does is determined in the child classes. A hydraulic engineer builds waterway facilities, and a defense engineer makes defense weapons. The role of the abstract class engineer is to act as a category that binds its children together. As I mentioned above, a hydraulic engineer or a defense engineer could fit into a position defined for engineer. Within a particular part of the program, when you write a code that instructs engineer to engineer, if you appoint a hydraulic engineer in the engineer's position, drainage will be built. And if you assign a defense engineer, defense facilities will be constructed. It's possible because the engineer's child classes must inherit and have a method called engineer. As such, another way to categorize different classes and assign the same responsibility is through an interface. In languages like Swift, it's called protocol, and there are languages like Python or Ruby that do not have this. Also remember that Go and TypeScript's interfaces are different from those in other languages. In my object-oriented videos, I will explain the interface in the way that is most commonly used, like in Java. An interface allows for different classes belonging to completely different parents to be grouped into one category. If inheritance is like receiving a family name from an ancestor, an interface is like a degree or a certificate. It can be granted regardless of lineage. Bats, flying fish, and pigeons, while each belonging to different classes like mammals, fish, and birds, all have the ability to fly. Therefore, they all implement the flying animals interface. The wagon driver interface is a certification that permits to transport materials using a wagon. You cannot create objects from the interface itself. It's like saying there's no job called wagon driver. All carpenters, bricklayers, and defense engineer need to transport materials with a wagon as part of their job. So, I will apply the wagon driver interface to these classes. It will be designated as a mandatory qualification for these jobs. Now, these four classes must implement this transport materials function in their own ways. For example, in the case of this construction carpenter, it acquires the attributes and methods inherited from the carpenter and also its own methods, along with the methods from the wagon driver interface. Also, they all come under a category called wagon driver. They can be elements in data structures made exclusively for wagon drivers, or they can be parameters in functions that take wagon drivers. In a situation where wagon drivers need to transport materials, any of these can be utilized, regardless of what type of object they are. And depending on what object is mobilized, how the transport materials is done will also vary. It's because, like the methods of an abstract class, each class that applies it implements it in its own way. In this video, we looked at various elements of object-oriented using the metaphor of castle construction. While listening to the explanation, some of you may have had various insights, and some of you may still not quite get what all this is about. Just remember the rough content for now, and as you watch the following object-oriented videos, you will be able to easily understand what the metaphors in this video are talking about. From now on, we'll explore object-oriented programming more deeply with actual programming code. I'll meet you in the next video on the topic of the solid principles. Following our last video explaining object-oriented programming with metaphors without code, in this video, we will explore the solid principles with examples of codes. Object-oriented programming is a concept that is complex to learn and utilize. Not only acquiring knowledge on the grammars and functions related to object-oriented, but there's also a lot of trial and error involved in using them effectively in the field. In sports like tennis, optimal breathing methods, hitting techniques, and movement postures are documented as regulations, which were found through the experiences and attempts of former players. When it comes to designing software with object-oriented programming, there are known 5 guidelines to make more efficient, robust, and easily maintained programs, which are known as the solid principles. The various patterns of the object-oriented that you will learn from the next video are also based on these principles. Just as there are various exceptional situations in a tennis game, although mostly adhering to these solid principles turns out to be the optimal choice, please remember in practice that there are times when flexibility needs to be demonstrated. Now let's look at each of these principles one by one. In this object-oriented design pattern series, I will draft examples using Java, a widely used programming language that includes the main syntax and features related to OOP. You can check out the sample codes on the Notion page linked in the pinned comment. If you are using other languages, you can copy the examples on the Notion page and easily translate them into your preferred language using generative AI. To follow this video, you should be familiar with object-oriented programming concepts such as classes, objects, methods, and interfaces in languages like Java. If you don't know about them, I just want to let you know in advance that it might be hard to understand the examples explained in the video. First, there is SRP, the Single Responsibility Principle. Exactly as it sounds, each class should only have one responsibility. In the previous video, we linked the classes to jobs. A carpenter works on woodworking, a mason handles stones, a blacksmith creates tools. We need to create classes to exist for one specific job.
Does each class need to have only one method?
Not exactly. Multiple methods can be used for one responsibility. However, the typical job a class carries out through these should be just one. Let's take a look at the sample code. First, here's a code that violates this principle. This user service class carries out 3 different tasks by itself. It saves a specific user's information in the database, it sends a welcome email to registered users, and even records each user's activities in a log. There are several issues with such code. First, the code of each class becomes complex, and it's difficult to intuitively understand their roles. Also, there are many reasons to modify each class, equal to the number of responsibilities it holds. A modification of one of those responsibilities could inadvertently affect the others. Because multiple responsibilities are intertwined in one place, testing and refactoring become tricky. There are also limitations in scalability and flexibility. Because these responsibilities are tied together, you can't just separate what you need and use it. Now, let's take a look at the code rewritten in compliance with SRP. As you can see, we've split the 3 responsibilities that were once packed into one user service into 3 separate classes. Just by looking at the names of the classes, you can guess what responsibilities each holds. A class responsible for storing user information, a class responsible for sending emails to users, and a class responsible for logging related to users can be easily identified. Each class only needs to modify its code when there are changes in the responsibility it has. And because classes are separated by responsibility, they are also easy to reuse as needed. In this way, the idea that each class is made with one task and purpose is the first one in the solid principles, which is the SRP. The second principle is the open-closed principle. This principle states that each class should be open for extension, but closed for modification.
The name of the principle doesn't quite connect with what it's saying. So, are you saying to extend the class rather than modifying it?
Yes, that's correct. Let's take a look at a sample code. It's a program that generates report documents as requested. The GenerateReport method of this class runs an if statement based on PDF or HTML given as an argument and generates a document in the corresponding format. In this sample code, only one line of code is written for each case like this. But in reality, very complex processes will take place here. Right now, we're only dealing with PDF and HTML formats, but what happens if we need to generate documents in other formats like XML in the future? This method will then have to be modified each time. As new cases are added, the code in this method will become more verbose and complicated. In that process, you could inadvertently affect the existing process, and there might be side effects in places where this method was already being used. Now let's look at the code applied with OCP. The function to create a document is made like this through an interface. It's an interface that defines the generate method. We don't write how the methods in an interface are performed. Just like this, methods name and form are only defined. The classes that apply this interface override this method and take responsibility to create documents in their own way. Now, if a new format is needed, you just create another class that applies this interface. In this way, you can design free from the issues that can occur during the process of modifying the existing code. The third is LSP, the Liskov substitution principle. LSP is the principle that a subclass should always be able to replace its superclass. To put it simply, a child should at least do everything the parent does. The place where the parent class object goes in should at least be able to perform the tasks the parent class used to do, even if the child class object gets put in that place. Let's take a look at this example code. In the parent class called bird, there is a method named fly. Because penguin is a subclass of the bird, it inherits this method. However, since the penguin is a bird that cannot fly, it cannot execute this method like the parent class. Fly, which works normally in the parent class, causes an exception in the subclass. Therefore, this becomes a wrong design. In such a situation, the fly method should not be a method inherited from the highest ancestor. It should be separated as an independent interface, as in the following example code. So, we are applying it only to those children of the bird class that can fly. The sparrow can fly, so it has implemented this interface, and you can see it's not applied to the penguin. So, there is no LSP violation in this code. Let's look at another example of violating LSP. This rectangle class has width and height properties, and it has setter methods to set these values. And this square class inherits from the rectangle class. Because a square is a kind of rectangle in geometry, this inheritance structure seems appropriate. The square class's setter methods for width and height don't take away functionality from the parent's methods, but instead add functionality like adjusting its height to match the width, so it seems like there won't be any problems. However, from a broader perspective, the square class does not have the functionality to specify different widths and heights, unlike the rectangle class. In the square class, when you modify the width, the height also gets modified, and vice versa. For example, if the width and height of a rectangle are set to 5 and 4 respectively, and the area is calculated, the output will be 20, but if you replace it with a square, the width set to 5 becomes meaningless, and 16 will be output.
So it's not just a matter of overriding methods.
Yes. Therefore, if you want to design such programs based on LSP, it would be desirable to remove the parent-child relationship between rectangles and squares, and make them separate classes applying the interface called shape. Now that the rectangle and square are separate classes implementing the shape interface, there's no problem. The fourth principle is the ISP, the Interface Segregation Principle. This principle is simple. It states that a class shouldn't be forced to implement methods it doesn't use. In the last lecture, we said that an interface is like a certification. If you had to know how to operate not only a regular car but also an excavator to get a driver's license, most people who get their driver's license would have to learn how to operate an excavator they will never use in their lifetime. Just as there are separate licenses for cars and excavators, interfaces should also be separated according to their responsibilities. Let's take a look at an example. This worker interface, designed to be implemented by factory workers, has work and eat methods. A class that implements this interface must implement these two methods. A regular human employee wouldn't have an issue performing both methods, but a robot does not eat. Therefore, if we introduce robot workers, this eat method would become redundant. Hence, we can separate this interface into workable and eatable, and allow regular employees to implement both, while robot workers only implement workable. Now, as long as the robotic employees only implement work of the workable interface, they don't violate the ISP. Lastly, we have DIP, the Dependency Inversion Principle. DIP is a principle that high-level modules should not depend on low-level modules, which might be hard to understand. Let's take a look at an example code. We have a fan class and a switch class. The switch class contains an instance of the fan class as an attribute, and when the methods to turn the switch on and off are executed, the fan operates and stops. Here, since the fan implements the specific action directly, it's a low-level module, and the switch provides abstracted logic to control this, making it a high-level module. However, in this code, the high-level module, the switch, is dependent on the low-level module, the fan. This is because the codes of the fan class, including the spin, stop methods, are being used as they are inside the switch class. If the names or parameters of these methods are changed, the run part of the switch class must be modified accordingly. Also, in such a structure, a switch can't handle other electrical appliances besides the fan. Therefore, in the modified code, we create a separate interface called switchable that has turn on and off methods. And the fan implements this interface, becoming part of the switchable category. Then, the switch treats the objects of the classes belonging to switchable as properties and executes their turn on, turn off methods internally. The switch and the fan do not communicate directly, but communicate through this switchable interface. Now, Any modifications to the fan's methods will not affect the switch class, and a switch can handle not only a fan, but also any other classes that implement switchable. With this, we have now covered all the solid principles. Each principle speaks to different aspects, but I believe you would have easily grasped what they collectively pursue. Remembering what you have learned in this video will assist you in understanding the object-oriented design patterns that you will learn later on. Starting with the next video, we will explore each of the major design patterns of object-oriented programming. Let's start reviewing the patterns of OODP now. If you connect to yalco.io, you can see this Notion page. Click on Object-Oriented Design Patterns in the Yalco Lectures section. And if you click on OODP Example Codes and Materials, you can view a list of the patterns we will cover, and by clicking on each, you can check the example codes used in the lectures. The example codes are all written in Java. This lecture assumes that you can understand code written in Java or similar programming languages like C# without any significant difficulty. If you are not familiar with object-oriented concepts and syntax such as classes, objects, static, and instance, abstract classes, and interfaces, I recommend that you get at least a brief understanding of these first. This list in the page categorizes the patterns by their type. However, in this course, we're going to study the patterns in a different order. In order to lower the entry barrier, I've planned to start from the easiest patterns, and to prevent boredom, we're going to cycle through different types of patterns. So, let's start with our first pattern, the facade pattern. The facade pattern is one of the easiest to understand, allowing you to implement it even if you don't know the syntax of an interface. Facade is a French term that refers to the exterior of a building. This pattern is similar to a drive-through service at a fast food restaurant. On the building's exterior, there's a window that takes orders and dispenses food. Inside the building, there are various areas for different purposes, such as a cash register, a cooking area, a drink machine, a wrapping station, but customers don't need to know about this internal structure as they receive all services through this window. Thus, the facade pattern is a pattern that makes it possible to use a complex system made up of multiple elements simply through a single interface. The code written in the facade pattern consists of a subsystem made up of multiple classes, a class that plays the role of facade, integrating these and providing a single window, and a client that uses functions through this facade. Now let's look at the first example. There are electronic devices such as a thermostat, lights, and a coffee maker in a house. In this way, each device is made as a class. The thermostat has the function of setting the house to a specific temperature. The light has the function of turning it on and off. The coffee maker has a method set up to brew coffee. When the owner of this house wakes up, they set the temperature, turn on the lights, and brew coffee. That means they have to manually operate each of these devices. Isn't there a way to have all of these actions performed by pressing just one button? The homeowner purchases a smart home system. This smart home facade class plays the role of the facade in this example. All the appliances I just talked about are connected to this smart home system. Like this, the objects of the classes created for each device are held as fields in this facade. In this way, each was brought in as a constructor and put into the corresponding field as a value. This system has two buttons on the wall that execute such methods. When you press the button that executes the wake up method, it sends commands to the connected devices to set the room temperature to 22 degrees, turn on the lights, and brew coffee. When you leave the house, you can press the Leave Home button to set the temperature to 18 degrees and turn off lights. Shall we take a look at the code of the main method, the execution part? In this lecture, we will call the class with a main method that runs the entire code as client. After creating objects of the temperature control device, lights, and coffee machine like this, and putting them as arguments in the constructor and creating an object of the smart home system, now you can simply issue commands through this facade called smart home. You can see these results in the code that presses the wake up button, and these results are output in the code that presses the leave button.
It's truly a simple pattern. It seems like a structure that people are already using a lot, even without learning it as a pattern.
That's right. This is also why we first dealt with this pattern. With the use of this facade, the client writing this main method doesn't need to know the details of the internal implementation of each of these subsystem classes, and can perform all the necessary functions through the integrated and simple interface of the facade. Even if the usage of the subsystem changes, you only need to modify the facade's code, not the client code. Thus, the flexibility of design is also improved. We will look at the second example now. There's a class for reading files, a class for writing files, and a class for deleting files. According to the first principle of Solid, we created classes for each responsibility. However, it can be quite cumbersome for the client to individually create and handle each of these three. We write the facade that combines all three into one class like this. This file system facade also has instances of the three classes we just saw as fields, but you can see that they aren't coming from outside, but are each directly created in the constructor like this.
So the facade takes care of creating the subsystem too.
Yes, and it has these three methods, each representing their functions. The method to read files executes the method of same name in the file reader. Similarly, you can see that the methods to write files and delete files execute the subsystem's methods. Shall we take a look at the code of the main class, which is the client now? As you can see, all you need to do is create and use this facade class object here. You can see that the classes of the subsystem are not used at all in this code. This facade class handles even the creation of subsystems objects internally. So with just this facade's object, you can issue all commands to create, write, and delete a file. You can use each function by calling the methods of the facade object like this. In this way, we examined the facade as the first pattern of OODP. It would have been a simple and easy pattern without any difficulty in understanding. I will see you with another pattern in the next video. The second pattern we're going to look into is the strategy pattern. This pattern sets up several methods or strategies for performing a particular task and allows them to be interchanged as needed. In other words, think of it as creating various modes of performing a task, each as a class, and selecting and using them as needed. Shopping carts are lined up in front of the cashier of a large supermarket. When it's their turn, all these carts perform a function called checkout. But there can be several ways to perform this function. You can pay cash, you can use a card, or you can pay through PayPal. All of these options are the modes and strategies for this method called checkout. Each of them becomes the specific algorithm of this checkout method. Now let's take a look at some code written to implement this. We first create an interface called payment strategy. As the name suggests, it's a strategy for making a payment. As you may already know, an interface just declares the names and types of methods. It does not write any implementations. The methods defined in the interface are implemented in the applicable classes. Here are two classes that implement the interface: credit card payment and PayPal payment. Applying the payment strategy interface signifies two main points. First, these two classes belong in the category named payment strategy. And second, they both need to implement the pay method of payment strategy in their own unique way. These classes, despite having a different number of fields and constructors, their objects can all take the place of payment strategy and are used for the purpose of running the pay method in that position. Next, let's take a look at shopping cart class. This class has the payment strategy interface as a field. So this is where one of the two classes that apply the interface could be fit in. And to allow for replacement with other strategies at any time, there is also a setter method like this. Also, when executing the checkout method of this class, it runs the pay method of the currently mounted strategy object.
The strategy could be thought of as different types of bullets, such as live rounds, paint bullets, rubber bullets, and this context is the gun.
Yes, it's one way to look at it. Then, this setter would be a method for loading bullets. Now, let's take a look at the main class which handles this gun. Firstly, create an object of the shopping cart gun like this. Then, use this setter method to set the strategy, that is, load the bullet. We first create an object of credit card payment and add it. The first calculation is done with a card. When you fire the gun named shopping cart with the selected strategy using the checkout method, the pay method implemented in the credit card payment class is executed, and this string is printed out. Let's modify the strategy this time. It's like loading a different bullet. You can create an object of PayPal payment like this in the same object, and if you run the checkout method again, you can see that it produces a result like this. This pattern separates several algorithms that perform specific functions into individual capsules, thus allowing them to be switched out at any point during code execution. If a new method needs to be added, you can easily extend by creating another strategy class, and it also becomes possible to reuse them in other places.
So, whenever something changes, I just need to modify the corresponding strategy, and if a different method is needed, I just make a new strategy. This would be code that adheres to the open-closed principle we learned from Solid.
You're exactly right. Now let's move on to the next example. The structure is exactly the same, it's just the content that's different, so let's take a quick look. It's a program that transforms a given string into another string using a specific algorithm. So in this interface, the compress method is declared, which takes a string as a parameter and returns a string. These two classes implement this method in different ways. The compress of the first class records the number of times each character in the string is contiguous and compresses it, while the compress of the second class transforms each vowel of the string into a predetermined number. The next class, compressor, is a context that fires their objects. Just like the shopping cart that we saw earlier, there's a field where strategy class objects go in, a setter that sets its value, and a compress method that executes the compress method of a strategy class object. Finally, this is the code for the client executing it. Here, this string will be transformed using the two strategies we've just examined. If you use the first strategy, run length encoding, you will get such a result, and if you use the next strategy, simple replacement compression, you can see this string being returned. You will easily understand if you look into the methods of these strategy classes in detail, each of which represents an algorithm. In this way, we've taken a look at the strategy pattern. If the concept of interfaces wasn't new to you, there wouldn't have been any difficult parts in this pattern. In the next lesson, we will get to know the template method pattern. The pattern we are going to discuss in this video is the template method pattern. This pattern is used when you need to implement tasks that need to be executed through certain predetermined steps. This pattern is useful when we need to ensure that the whole process is executed in a specific order, although we can implement how we perform each step in various ways. Think about dining at a French restaurant. A typical French meal consists of these courses. If it's the high-end restaurants that value tradition, they would serve food in this particular order. There can be various food items served in each stage. For the hors d'oeuvre, a salad, smoked salmon, or snail dishes could be served. For dessert, tart, crème brûlée, or macaron could be served. Depending on what menu is chosen for each stage, you can have numerous combinations, but to be recognized as a traditional French restaurant, you must adhere to this order defined as an abstract class. This is the template you have to follow. Now, let's look at some examples. Assume there's a process of making hot beverages like coffee or tea. We'll assume that whatever the drink is, it goes through a common process of boiling water, brewing the drink, pouring it into a cup, and adding condiments. For this, we'll create an abstract class like this, while an interface allows you to only declare each method without implementation. An abstract class allows you to write the implementation of the methods you want. A method for boiling water, a method for brewing the drink, a method for pouring the drink into a cup, and a method for adding condiments are either just declared or fully implemented like this. The reason why we need to use an abstract class instead of an interface is this prepare recipe method. This method must have an implementation like this. This method acts as the template method in this program. Here, you can see that the mentioned methods are being called in this order. So, this becomes the template of this program. Shall we now look at the classes that have actualized this? There are the tea class and the coffee class. Only the brew method and add condiments method, which are not implemented in the beverage class, are implemented here in their own ways. Regardless of how these classes implement their respective methods, the brew method comes after the boil water method, and the add condiments method comes after the pour in cup method. Shall we take a look at the client code lastly? I told you, abstract classes and interfaces become categories for classes that extend or apply this. So, you can put tea and coffee objects in a variable of beverage type like this. Firstly, let's try to invoke the prepare recipe method from a tea object. As you can easily predict, these methods are invoked in order, and you can see that such a result is output. It's the same even if you run it with a coffee object. Thus, the template method pattern can be useful in cases where the structure of the algorithm to be implemented is fixed, but each detailed process can be changed or expanded. Let's take a look at a more practical example this time. It's a program that reads files of various formats such as JSON, XML, CSV, processes them, and then saves them in other forms. Like this, you load the file, check if the file is written in the correct format, process it according to a predetermined algorithm, and then save it as a new file.
So, this process method is the template. Here, instead of just executing these in order, it uses a conditional statement based on one of them.
Yes, the template method can be used in this form. After loading the file, depending on the execution result of the method that checks if the file format is correct, it either executes the remaining two methods or produces an error message. Now, these are the two classes that inherit from this abstract class. Each of them implements the process of handling CSV data and JSON data respectively. The validity of data is determined by whether the given string as a parameter includes CSV and JSON respectively. The remaining part is just code that prints out the process, so pause the video and take a look at the code if needed. It shouldn't be hard to imagine how this code is used by the client and how the results come out. Like this, you create instances of these two concrete classes and you run them by calling the template method named process. If the data you input matches the format represented by the object, all the processes are run and such a result is output. In this way, when you put XML data into a JSON data processor, you can see that this message is displayed. Thus, we have examined the template method pattern. If you keep this pattern in mind, you will have times when you find places where it can be useful in the field. In the next video, we will look at the very famous and also useful pattern, Singleton. In this video, we are going to delve into the Singleton pattern. Singleton is one of the particularly unique and important patterns in OODP. This pattern is necessary when in a program, a particular class's object should be created only once. To understand this pattern, you need to know about static members. Elements of a class, namely fields and methods, consist of instance elements and static elements. Instance elements are created with each new instance, that is, an object of the class, and they take up memory space. However, static elements are created only once, regardless of the number of created objects. Let's assume there's a hamburger chain called Jalkoburger. We can define a class representing Jalkoburger like this, and we can create instances, in other words, objects of them. A class can be compared to the chain itself, and each object can be likened to the stores located here and there. Among the fields this Jalkoburger class has, the ones without the static are instance fields, which are data belonging to each object, that is, store. Store location, manager's name, and the presence of a drive-thru are data that should exist in each store. They must be created as many as the number of objects and stored in memory. On the other hand, static elements are part of the chain Jalkoburger itself. They're not data belonging to a particular store, which is why only one of them is needed, like the brand name and the CEO's name. Since this isn't a programming language class, I'll stop explaining about static here. Now, let's look at why this concept of static is needed in Singleton pattern. Sometimes you need a type of data that can exist in only one instance in a program. For example, like the dark mode status in a program that provides UI. This data should be applied uniformly throughout the program, so it becomes problematic if it's stored in more than two places, because buttons could be in dark mode while text fields remain in white mode. Different theme modes should not coexist within a single screen. Therefore, a static boolean named isDarkMode like this would suffice for such a purpose. And if other fields and methods need to be included in this theme settings, you can define a class like this and then its object. The problem is that an object of a class can be created as many times as you want unless you take any measures. We need to make sure that this theme class object is never created more than once in the program. The technique used for this is called Singleton. Now, let's look at an example applying the Singleton pattern. Interestingly, in this theme class, a private access modifier is attached to this constructor. This is to completely prevent the use of this method outside of this class code. It's as if the chain has blocked off chain applications. From the outside, you absolutely can't create an instance, an object of this class. Because you can't use its constructor, then how do we create and use an object of the theme class? First, let's look at this field called instance. As you can see, it's a static field that can only exist one in the program, and its data type is the class itself, the theme. The only object of the theme class is stored right here. It's like having the only store of the chain housed in the chain's headquarters, and the code that creates this object is in this method called getInstance. Since it's a static method, it is called not from an instance, but from the class itself, and this method is the key part in Singleton Pattern. Firstly, this method checks if this instance static field is null. It should be null at the first execution, because no value has been assigned yet. If it is, it creates an instance of this theme class itself through the constructor and assigns it to the field. It's possible since even a constructor with private access can be used within this class. Normally, we need to add some synchronizing related codes for multi-threading environment, but since this is not a Java tutorial, I'll stop here. After this getInstance method is called once, this instance field will no longer be null, so this part will not run anymore. This method returns the instance field, which is created and assigned only once, like this. Because the constructor is written like this, the initial value of the theme color field will be light. Later, this setThemeColor setter method is used to change the value. So it's a method that changes the theme color field of a theme instance, which exists uniquely on the program. On the contrary, this getThemeColor method is a getter to access that value. Now here's the code for the classes that require this theme color. UI elements like buttons, text fields, and labels are each made into classes. The part to pay particular attention to is this code. Please pause the video for a moment and focus on this section of the code. When you run the display method, which means to render each element on the screen, it fetches the color specified in the current theme settings like this. As we designed it, this theme class is a singleton, so it accesses the unique instance via getInstance, a static method, and uses this getter to get the value of the theme color field. The rest of the code parts are not so crucial in this example. Now, let's examine the client code. The button, text field, label classes we just saw are not singletons, so they're created using a constructor like this. And then we execute each display method like this. This is the very method that uses the value of the singleton class we just looked over in the previous code. As a result of executing this method, you can see such a result appearing. The light value retrieved from the singleton object, which we just looked at specifically in these parts. It appears as a result like this. It's not confirmed at this point, but we can infer that all these values came from a single object. Now, let's verify this. In this client code, we access the only object of the theme class using the getInstance method, and then we change the value of theme color to dark using the setter method this time. After that, if you run the display method on the objects of the button, input field, and label again, you can see that results like these are output. In this segment, the value light was embedded in all the strings, but as you can see, after modifying the field value of the singleton object, all of them were output as dark. This implies the theme class objects referred to in this segment are all the same, a single instance. At this point in the client code, where the display method is first called through the object of button. In other words, when the getInstance method of the theme class was first called right in this method, the creation of the singleton object occurred only once, and since then, that unique object has been continuously returned and used. If you look carefully at the sample codes on the Notion page again, you should be able to understand it without difficulty. Now, by utilizing this singleton class, we can prevent the issues that arise when more than two instances of any class exist. If you're using a different language, you can translate this code with an AI tool to examine it. This singleton may be written in many different ways due to differences in syntax among languages. But if you remember the principles and key points we learned in this video, you can easily understand code in other languages. In the next video, we will explore the state pattern. The pattern we are going to learn this time is the state pattern. In this pattern, a state of something exists as an object of its corresponding class. For example, with a door, open state and closed state each exist as a class. The door has the function to open and close, and the execution result of these functions changes depending on the current state of the door. Let's go straight into the example code. There is an interface named state like this. There are declared methods for opening and closing the door. Now let's create a closed state class and open state class that apply these interfaces. Each represents the state of the door being closed and opened respectively. You can also see that the open and close methods defined in the interface are implemented differently like this. In other words, the way to execute given methods is differently implemented for each state. There's another class called door. As you can see, it has an instance of the state interface as a field. So this state, like closed or open, is contained as the attribute of this door. Initially, the closed is initialized. It starts with the door being closed. What happens if you give the close command in this state? Since the door is closed, the close method of closed state is executed. This method only prints a message that the door is already closed and ends. So, how about we execute the open method? Execute the setState method of door by creating and inputting an instance of openState as an argument. That is, it's about changing the status of the door to open. Now, when the open and close methods are executed in door, what is implemented in the openState object is executed. If you try to open the door again in this state, a message that the door is already open is printed out. And if you give an order to close the door, it changes the status back to closed. Whenever you transition from one state to another, you can see that a new object of the target state is created and put in with the constructor. When transitioning from an open state to a closed state, you create an object of closed. And when transitioning from a closed state to an open state, you create an object of open and put it in door.
If I didn't use this pattern, I would have had to implement it with an if statement for each state, right?
Yes, that's right. As the states diversified, the conditional statements would have become much more complex. Now, when the client code creates an object of the door and executes the open and close methods, the result that will appear is not difficult to predict. The status of the door is initialized to closed at the point of creation, and it's not hard to understand that it transitions to the open state at this point, and then returns to the closed state from here. And the messages from open and close methods are printed like this, according to each state. Like this, the state pattern separates something's state into classes for each value. Each of these states implements methods in their own ways, and when necessary, they change themselves into different states, reducing code complexity and increasing flexibility. Now, let's take a look at the second example. It's a program that describes the operation of a video player with the state pattern. The state interface in this example has play and stop methods, and the three states of stop, playing, and pause are each defined as separate classes. You can think of it as toggling back and forth between these three states with a remote control that only has a stop and play button. The video player class that uses these states has the same structure as the door class in the previous example. Therefore, I won't explain this code separately. Now let's take a look at how play and stop work in these three states. First, the stop button in the stop state does nothing. You can see that it just outputs a message saying it's already stopped. When you press the play button, it switches the state to playing. From that point on, the methods of playing state are to be executed. You can also see here that we're creating and using an object in the playing state. As you might expect, the play button in the playing state does nothing. And if you press the stop button while playing, it will initially go into this paused state. In the paused state, both buttons perform meaningful actions. If you press the play button, it will be back to the playing state. On the other hand, if you press stop once more, it will move to a completely stopped state. The client code is also like the door example we saw earlier. As written in the constructor of video player, the initial state is stopped. When you press the play button, it immediately goes into playing state. If you press stop, it becomes paused. If you press the play button again to return to the playing state and press stop once, it becomes paused. And if you press stop again, it fully stops. If you did not use the state pattern and wrote the code with conditions, it would have looked like this.
The total code length has been reduced, but as the states and conditions get complicated, this part also becomes complicated to write, and it seems like there will be more room for mistakes.
You're right. You need to remember that short code is not always good code. By using this state pattern, we can flexibly manage actions depending on the changes in object state, and you will be able to write readable code without complex conditional statements. Next time, we'll take a look at the adapter pattern. I hope the knowledge I have shared with you so far through this video has been helpful. If you liked my lecture, you can purchase the full course by visiting the link I posted in the pinned comment. In addition to what I've shared in this video, you will learn about 20 other patterns. Once you have completed the full course, you'll know a total of 25 patterns. After learning all of these, you will freely apply the appropriate pattern to the software you develop, resulting in a much more efficient and solid design. I promise this will be a course worth your time and money. Well, I'll see you in the lecture. Happy coding!